Now let's draw the third possible connection of delta star connection. In third and fourth possible connection of delta star connection, now we will have the changes in HE winding connections. That is, in first and second possible connection, we join the non-dot end terminal with dot end. And now in third and fourth possible connection, we will join the dot end terminal with non-dot end terminal. This is the only change that we are making in primary side, that is in HV side. And now coming to the LV winding connection, in third possible connection, we will join the non-dot end terminals and take the output from dot end terminals. And in fourth possible connection, we will join the dot end terminals and we will take the connections from non-dot end terminals. Now let's see the third possible connection of delta star connection. Let these three be the primary side HV windings, and let these three be the secondary side LV windings. And here on primary side we are having delta connection. In first two possible connections, we join the non-dot end terminal with dot end. Now in coming two cases, that is in third and fourth possible connection, we are joining the dot end terminal with non-dot end, dot end terminal with non-dot end, dot end terminal with non-dot end. So this is the HV winding delta connection. And now coming to the LV winding, which is a star connected, and here we are taking the common connections as A1, B1 and C1. So let's join that and take the connections from A2, B2 and C2. And now let's draw the phase diagram for this connection. First, let's draw the phase diagram for primary side delta connected winding. Let us suppose this is the VA phasor, and now let's decide the terminals of this primary side VA phasor as arrow points towards the connection we took from. So that is here A2, therefore this will be A1. Now observing primary side winding connection that to A2 there is B1 connection and to A1 there is C2 connection. And we know that in three-phase ABC phase sequence system, VA will be at an angle 0 degrees and VB will be at an angle minus 120 degrees and VC will be at an angle minus 240 degrees. Therefore, let's draw the VB phasor at an angle minus 120 degrees, okay, from VA. So if this is the VA phasor, now in clockwise direction, because minus 120 degrees, so in clockwise direction at an angle minus 120 degrees, there will be VB phasor. So let's consider this as VB phasor, and observing winding connection that on primary side the external connections are took from dot and terminals. Therefore, arrow must point towards dot and terminal. Therefore, this must be B2 and other end must be B1. So now place this VB phasor such that this A2 will have B1. Therefore, VB phasor will be like this. This is B2. And now let's draw the primary side Vc Phasor, which will be at an angle minus 240 degrees from VA, or we can take at an angle minus 120 degrees from VB. Therefore, as this is the VB phasor, so in clockwise direction at an angle minus 120 degrees, let's draw VC. So VC will be in this direction like this. So let's consider VC like this, and let's give the notation C1 and C2, and observe in primary winding connection that C2 is the terminal from which we are taking the connection. So C2 must have arrow, therefore like this. Now observe winding connection that to V2 there is C1 connection, means here we must have C1, and to A1 there is C2 connection, means here C2. Therefore place this phasor here such that B2 will have C1. Therefore this is the phasor diagram for delta connection on primary side. And here in delta connection we need to decide the phase neutral voltage for reference purpose, because it is on HV side, and we know that there will be no neutral connection in delta connection, but for reference purpose we need to consider the neutral connection. So here we are considering the imaginary neutral connection. As this is HV side, let's consider that with capital N. And now we need to decide the of A2N and A1N, which is the phase neutral voltage. So observing primary winding connection that the external connections are took from A2. Therefore Here the reference phase neutral voltage will be A to N. So this is the phasor diagram for this type of delta connection. Now let's draw the LV winding phasor diagram. And we know that the secondary side phasors are drawn parallel to primary side phasors. So let's draw the secondary side VA phasor parallel to primary side VA phasor. So let this be the secondary side VA phasor parallel to primary side VA phasor. Now let's decide the direction of secondary side VA phasor. So which depends on the connections we took on primary side and secondary side. So observe that on primary side the connections are took on dot and terminals, and on secondary side the connections are took on dot and terminals. Therefore the secondary side VA phasor direction will be same to that of primary side VA phasor. So like this. Now let's decide the terminals of the secondary side VA phasor. As the connections are took from dot and terminals, that is A2, therefore arrow will point towards A2. So other end will be A1. Now let's draw the secondary side VB phasor. So drawing secondary side VB phasor parallel to primary side VB phasor like this. Now let's decide the direction of secondary side VB phasor. As the connections on primary side and secondary side are took on dot and terminals, therefore secondary side VB phasor direction will be same to the top primary side VB phasor. So like this. Now let's decide the terminals of the secondary side VB phasor. So as the connections are took from dot and terminals, therefore arrow will point towards the B2. So other end will be B1. Now observing winding connection that to A1 there is B1 connection, means to A1 there must be B1. So now draw this secondary side VB phasor such that A1 will have B1 terminal. Therefore this will be B2 and this is B1. Now let's draw the secondary side Vc Phasor. So let this be the secondary side Vc Phasor drawn parallel to primary side Vc Phasor. And now let's decide the direction. So as the connections on both primary side and secondary side took on dot ends, therefore secondary side Vc Phasor direction will be same to that of primary side Vc Phasor. So like this. Now let's decide the terminals of this secondary side Vc Phasor. So as the connections are took from dot and terminals, so arrow will point towards dot and terminal, that is C2. So this is C1. And observing winding connection that to A1 and B1 there is C1 connection, means here we will get C1. So draw this phasor such that A1 and B1 will have C1 terminals. So like this. This is Vc Phasor and the end will be C2. And now let's give the common notation for this common connection. Let that be small n. Now let's identify the vector group symbol for this type of connection. And it is known that the first character in vector group symbol is in capital letter, and that will indicate the HV winding connection. And here we took the HV winding as delta. So to represent that, the first character in vector group symbol is capital T. And the second character in vector group symbol is in smaller case, and that will indicate the LV winding connection. And here we took the LV winding connection as star. So to represent that, it is represented in small y. And now we need to decide the third position of vector group symbol, which is a numerical, and that numerical is obtained by clock notation. And to obtain that, let's observe these phasor diagrams, because that numerical will indicate the LV winding phase to neutral voltage displacement with respect to HV winding phase to neutral voltage. So we need the LV winding phase to neutral voltage and HV winding phase to neutral voltage. So in star connection, that is in LV winding, here the phase to neutral voltage is small a to n, and on HV winding the phase to neutral voltage is capital A to n. And it is studied that the HV winding phase to neutral voltage is represented with minute needle in clock and is always taken as a reference. So it is always shown pointing towards clock. And now to know the numerical, let's superimpose this diagram on this diagram and observe the phase to neutral voltage of HV winding and LV winding. So if you superimpose, then HV winding phase to neutral voltage and LV winding phase to neutral voltage will look like this. And it is also studied that the LV winding phase to neutral voltage is represented by hours needle in clock. Okay, so now if you place this diagram in clock such that the HV winding phase to neutral voltage points towards 12, so then the diagram will look like this. So now the hours needle will be shown pointing towards 1, means the numerical in vector group symbol will be 1. which will indicate the LV winding phase neutral voltage displacement with respect to HV side phase neutral voltage, and that is obtained by the angle between minutes needle and hours needle. So for one, the angle between minutes needle and hours needle is 30 degrees, and as this angle is measured in clockwise, so it is given negative sign. From this we can say that with this connection we are obtaining 30 degrees lag phase displacement. Now let's obtain the fourth possible connection of delta star connection, and in that what we are doing means we are leaving this connection as it is, and the change what we are making is here is only on secondary side. So instead of joining the A1 B1 C1, we will join A2 B2 C2 and take the connections from A1 B1 and C1. Now let's see that. In fourth possible connection of delta star connection, what we are making that on secondary side we are joining the dot-end terminals, that is A2 B2 and C2, and taking the connections from non-dot-end terminals, and HOID connections we left as it is. So the phasor diagram is same. And now let's draw the phasor diagram for LV winding connection. Okay, so the secondary side phasors are drawn parallel to primary side phasors. So let's draw the secondary side VA phasor parallel to primary side VA phasor. So okay, like this. Now let's decide the direction of secondary side VA phasor, and which depends on the connections we took on primary side and secondary side. So on primary side connections are took from dot ends, and on secondary side connections are took from non-dot ends. Means the secondary side phasor direction will be opposite to primary side VA phasor. So as the primary side VA phasor is upwards like this, therefore the secondary side VA phasor direction will be like this. Now let's decide the terminals of this secondary side VA phasor, and here we are taking the connections from non-dot end terminals, that is A1. Therefore arrow will point towards A1, so other end will be A2. And now let's draw the secondary side VB phasor. So let's draw the secondary side VB phasor parallel to primary side VB phasor somewhere here. And now let's decide the direction, as the connection on primary side is from dot end terminal and the connection from secondary side is from non-dot end. Therefore the direction of secondary side VB phasor will be opposite to primary side VB phasor. So as the primary side VB phasor is towards this direction, so secondary side VB phasor direction will be like this. Now let's decide the terminals of VB phasor, and observe that here the connections are took from non-dot end terminals. Therefore arrow will point towards B1, the other end will be B2, and observe by the connection that A2 is having B2. Therefore to A2 we must have B2. So place this VB phasor such that A2 will have B2 terminal. Therefore the phasor is like this. This is B1. Now let's draw the secondary side Vc Phasor. Let this be the secondary side Vc Phasor drawn parallel to primary side Vc Phasor. Now let's decide the direction of secondary side Vc Phasor. As on primary side the connections are took from dot ends, and on secondary side the connections are took from non-dot ends. Therefore secondary side Vc Phasor direction will be opposite to primary side Vc Phasor. Therefore the direction will be like this. Now let's decide the terminals of Vc Phasor. So as the connection is took from non-dot end terminal, that is C1, therefore arrow will point towards C1 and the other end will be C2. And observing by the connection that to A2 and B2 there is C2 connection, means here we must get C2. So draw this phasor such that A2 and B2 will have C2. So like this. This is Vc Phasor which is having C1 terminal. So now let's identify the vector group symbol for this type of delta star connection. Okay, and we know that the first character in vector group symbol is D, because the HV winding connection is delta, and the second character in vector group symbol is small y, because the LV winding connection here is star connection. And now we need to design the numerical in vector group symbol for this type of connection. For that, let's superimpose the LV winding phasor diagram on HV winding phasor diagram and observe the HV winding phase neutral voltage and LV winding phase neutral voltage. So if you observe that HV winding phase neutral voltage will be like this, and LV winding phase neutral voltage will look like this. And it is studied that the HV winding phase neutral voltage is represented with minutes needle in clock, and that is taken as a reference, so it is always shown pointing towards 12, and LV winding phase to neutral voltage is represented with hour's needle in clock. Okay, now if you place this diagram such that this HV winding phase to neutral voltage will point towards 12, then the diagram will look like this. Means the hour's needle is shown pointing towards 7, and these corresponding positions represents 7 o'clock, which means the numerical in vector group symbol for this type of connection is 7, which will indicate the LV winding phase to neutral voltage displacement with respect to HV winding phase to neutral voltage, and that is given by the angle between minutes needle and hour's needle. The angle between minutes needle and hour's needle is 150 degrees, which can be written as 180 degrees minus 30 degrees. So these are the 4 possible connections of delta star connection, from which we got the 4 different phase displacements, that is plus or minus 30 degrees and 180 degrees plus or minus 30 degrees. Now let's know the phase voltage ratio and line voltage ratio, and we know that phase voltage ratio can be taken as equal to transformation ratio constant K, and which is same as that of single phase transformer, and that can be taken as equal to N2 by N1, where N2 is the secondary side number of turns and N1 is the primary side number of turns. So if small v2 is secondary side phase voltage and small v1 is primary side phase voltage, then the transformation ratio constant K can be taken as equal to small v2 by small v1. Now let's find out the line voltage ratio, which can be taken as equal to K or not. That depends on the connection employed in 3-phase transformer. So let's find out the line voltage ratio for delta star connection. Let capital V2 be secondary side line voltage and capital V1 be primary side line voltage. Therefore, line voltage ratio can be taken as equal to capital V2 by capital V1. Now observe the secondary side winding connection, which is a star, and the relation between line voltage and phase voltage for star connection is line voltage is equal to root 3 times phase voltage. So for secondary side, that is for star connection, okay, secondary side voltage V2 is equal to root 3 times the secondary side phase voltage. And coming to the primary side connection, which is a delta, so the relation between line voltage and phase voltage for delta connection is line voltage is equal to phase voltage. So line voltage V1 is equal to phase voltage small v1. So these are the voltage relations. Now let's replace the line voltages with phase voltages. So that will give you root 3 times small v2 by small v1. So that will give you root 3 times K, because we know that small v2 by small v1 can be taken as equal to transformation ratio constant K, and that is equal to 1.732 times K. So from this relation we can say that delta star connection can provide a secondary line voltage which is 73.2 times the primary side line voltage for K is equal to 1. In simple, we can say that delta star connection can provide more voltage, that is 73.2 times the primary side line voltage. Therefore, delta star connection is used for high voltage applications. Therefore, the advantage of delta star connection is that used for 3-phase 4-wire system, because star can have neutral connection. Therefore, we take neutral connection, and as this connection is having delta connection, so no distortion in secondary side voltage, that is no harmonics problem. And the third advantage is it can handle large unbalanced loads. These are the main advantages of delta star connection. And now let's see the disadvantages of delta star connection, and the disadvantage is that it can't be paralleled with transformers having different phase displacements. And the applications are, and we studied from the line voltage relation of delta star connection that secondary side line voltage is equal to root 3 times K into primary side line voltage. Means delta star connection is used for high voltage applications, and the other advantage is this is mostly used connection, because on secondary side, as it is having star connection, it can be used for supplying the 3-phase 4-way system. Okay, so this is about star delta connection.